Hello students, in today's class we are going to discuss about transistor biasing. So first we discuss about the definition and purpose, second that inherent variations of transistor parameters, third stabilization, fourth the need for stabilization, and fifth essentials of a transistor biasing circuit, and sixth one is the stability factor. So first we have to discuss about what is the definition of transistor biasing. So we learned in the previous session that for faithful amplification, three conditions must be satisfied. First one is the proper zero signal collector current. Second one, proper minimum VBE at any instant. And third one, proper minimum VCE at any instant. So transistor biasing means the proper flow of zero signal collector current and maintenance of proper collector emitter voltage during the passage of the signal is known as transistor biasing. So why do we need to bias a transistor, or why do we need transistor biasing? So the basic purpose of a transistor biasing is to keep VBE always forward biased and VCE always reverse biased. So transistor biasing is needed to make or to satisfy this condition. So by transistor biasing we can ensure that the input circuit is always forward biased and output circuit is always reverse biased. So this we already done in the previous session. That means the faithful amplification is achieved by biasing, by inserting a battery in the input circuit. So it is one way of biasing the transistor. So there are two types of transistor biasing, or two types or methods of transistor biasing. So first method is, we already introduced that is first method is by introducing a bias battery. By inserting a battery in the input circuit will make the transistor biased, or it will ensure that the input circuit is always forward biased and output circuit is always reverse biased. So first method of transistor biasing is bias battery, and second method of transistor biasing is associating a circuit with a transistor, and this circuit is known as biasing circuit. So biasing circuit is the circuit which provides transistor biasing. So these are the two methods of transistor biasing. So using any of these two methods, we can ensure that input circuit is always forward biased and output circuit is always reverse biased. Then the transistor will be in the active region, and transistor can act as an amplifier, and it can do faithful amplification. So this is about transistor biasing. Now we are discussing about the inherent variations of transistor parameters. So which are the transistor parameters undergoing variations? You all are familiar with the transistor parameter beta. What is beta? Beta is the current gain. Beta is the current gain. Current gain means output current by input current. In the case of common emitter amplifier, beta is equal to IC, output current by input current IB. So beta is equal to IC by IB. So beta is one of the transistor parameter, and another parameter is VBE. VBE is the base emitter voltage, or voltage in the base emitter junction. So you can see that in practical cases, these two transistor parameters, beta and VBE, are not the same for every transistor, even of the same type. So what do you mean by same type? Suppose I am using a transistor BC107. This transistor is used in our lab for doing the experiments of using transistors. So BC107 is a type of transistor used in the lab. So this is a transistor type, and it has some significances which we will discuss in the lab session. So BC107 type transistor, if we take two transistors of same type, that means of same type BC107, it will have or it will show variation in beta and VB value. That means even if the transistor is of the same type, these two parameters beta and VB will change. The main reason for this variation is that transistor manufacturing technique is very difficult, or we need much advanced technique or much sophisticated technique to make the transistor parameter invariant. So we don't have much sophisticated technique or manufacturing technique. So in practical cases, beta and VB shows variations. So for example, the base width may vary from one transistor to another one, even of the same kind. These variations result in large change in transistor parameters of beta and VB. We know that base width is a main factor in determining the depletion layer or depletion width. It will affect VBE, base width will affect IB. So if IB is changing, beta will change. If VB is changing, if base width is changing, VB will change. So that means beta and VB are two crucial transistor parameters which show inherent variations even in the manufacture. So these variations of transistor parameters will change the operating point Q. So the change in beta and VB will change Q point. So what will happen if operating point is changing? It will lead to unfaithful amplification. So you have to note that Q point has much significance. The variation in Q point should be stable. If Q point is changing, it will result in unfaithful amplification. So to make the amplification faithful one, we need a biasing circuit which can work with all transistors of same type. That means Q should be independent of Q point. That means operating point should be independent of transistor parameter variations. This is an important point you should be kept in mind. Transistor parameter variations. So even if the transistor parameters are varying, it should not make any change in the Q point. So Q point should be independent of transistor parameter variations. So now our aim is to make the transistor parameter or to make the Q point independent of transistor parameter variations. So how can we make Q point independent of transistor parameter variations? So the process of making Q point independent of these variations is known as stabilization, which we will discuss in the next session. So here we studied about inherent variations of transistor parameters. We have two transistor parameters, beta and VBE. These two transistor parameters have the inherent property that due to their manufacturing technique, because they are not using any advanced techniques for manufacture, there are some variations in the base width. In manufacturing the base width, it will affect beta and VBE. So change in beta and VB will result in a change in Q point, which will lead to unfaithful amplification. So we have to make Q point independent of transistor parameter variations. So the process of making the Q point independent of transistor parameter variations is known as stabilization. So stabilization can be defined as process of making Q point or operating point independent of independent of two things. So what are the two things affecting the Q point? So Q point, we know that what is Q point? Q point is the zero signal, collector current and VC value. So this is known as Q point. So if IC is varying, it will affect Q point. So IC will vary when two things are happening. First one, when inherent variations of transistor parameters occur. Inherent variations of transistor parameters. Second point is that IC will vary when the temperature changes. It is an important concept. IC depends on, or IC will change when the temperature changes or when inherent variations occur in inherent variations of transistor parameters occur. So we have to make Q point independent of IC, which means that we have to make operating point independent of these two changes. So the process of making operating point independent of temperature changes or variations in transistor parameters is known as stabilization. So we can define stabilization as the process of making operating point independent of temperature changes or variations in transistor parameters. So why these 2 points happening? These 2 points will change or will cause the IC to change. If IC is changing, Q point will change. So the need for stabilization, we are discussing in the next topic, why we need stabilization. So we already discussed 2 points why we need stabilization. We need the operating point independent of Q point variation, or the process of making Q point independent of Q point variation is called stabilization. So we need stabilization due to 3 things. First one, temperature independence of IC. Temperature independence of IC. Second one, individual variations or inherent parameters, inherent variations of transistor parameters. Then third one, thermal runaway. Second one, individual variations or inherent variations. And third one, thermal runaway. We will discuss each point in detail. Thermal runaway. So what is the temperature dependence of IC? So what is the temperature dependence of IC? So first we are discussing about that. Temperature dependence of IC means that we know the expression for IC. What is the expression for IC? IC is equal to, in the case of common emitter amplifier, IC is beta IB plus ICEO, that we discussed. So ICEO can be written in terms of alpha, that is beta IB plus ICBO by 1 minus alpha, that is ICEO. So it can also written in terms of beta, that is IC is equal to beta IB plus 1 by 1 minus alpha is beta plus 1. So 1 by 1 minus alpha can be replaced as beta plus 1, ICBO. So the expression for IC in terms of beta is IC is equal to beta IB plus beta plus 1 into ICBO. So what will happen when temperature changes? When temperature increases, what will happen? When temperature increases, minority carriers increases. Minority charge carriers increases. if minority charge carriers are increasing, leakage current increases. Because we know that leakage current is the current due to the flow of minority carriers. So as minority carriers are increasing, we have more leakage current. So that means this term beta plus 1 ICBO is increasing, or ICBO is increasing. So this causes the IC to change. So we can say that when temperature increases, IC increases. So we have to stabilize the circuit. That means even when the temperature change, IC should be made independent, or we have to make Q point independent of these variations. That is the need of stabilization. Now see the second point, individual variations, that we already discussed. Individual variations means variations in the transistor parameter of beta and VBE. Transistor parameters beta and VBE are not exactly the same for any two transistors, even of the same type. So when a transistor is replaced by another one, these variations changes the operating point, and so we need to stabilize this, or we need to stabilize the Q point. Now third point is thermal runaway. So we can discuss this point, thermal runaway. We have seen the expression for IC. IC is equal to beta IB plus beta plus 1 ICBO. So the collector leakage current ICBO is strongly dependent on temperature, that we will see from here. Temperature is when temperature will change, ICBO will change. When temperature is increasing, the leakage current will increase. So ICBO is increasing. So when the leakage current increase, what will happen? It produces heat within the transistor. So ICBO will produce heat within the transistor. ICBO produce heat. So when there is heat production in the transistor, it means that the transistor temperature is increasing. So what will happen? When the temperature is increasing, when transistor temperature is increasing, it will eventually make the transistor to burn out, because IC is increased by beta plus 1 ICBO. So finally the transistor will damage, or transistor will destroy, and this self-destruction of transistor is known as thermal runaway. It will lead to, so the temperature change or temperature increase will lead to self-destruction of unstabilized transistor. Because our transistor is not stabilized, so due to this unstabilization, it will cause the unstabilization of transistor, or self-destruction of transistor, and it is known as thermal runaway. So thermal runaway is caused due to the temperature change, and the temperature change will lead to production of heat within the transistor, and it will cause the self-destruction of unstabilized transistor, which is known as thermal runaway. So we need to avoid this, so we need stabilization. So we discussed 3 points. First one, temperature dependence of IC. It is clear from here. That means when temperature change, it will change the minority carriers and it will increase the leakage current. So IC will change. Next one is inherent variations of transistor parameters, beta and VBE. And third one is thermal runaway. So due to large leakage current, temperature increases within the transistor and produce heat, and it will lead to self-destruction of unstabilized transistor. So now we discussed need for stabilization. Next, we are going to discuss about the essentials of transistor biasing circuit. This is important. Essentials of a transistor biasing circuit. So we already see about transistor biasing circuit. What do we mean by biasing circuit? The circuit which provides transistor biasing is known as transistor biasing circuit. We need to remember 3 points. So while making a transistor biasing circuit, we have to take care of 3 points. So these are the 3 essential points to be taken care while making a transistor biasing circuit. First one, the biasing circuit should ensure proper zero signal collector current. Proper zero signal collector current IC. Second point is that we have to ensure that the biasing circuit should ensure that VCE should not fall below 0.5 volt for germanium and 1 volt for silicon transistors at any instant. That means it should ensure that, or it should ensure proper minimum VCE at any instant. And third one is it should ensure the stabilization of Q point. It should ensure the stabilization of Q point. So these 3 points should be noted while making a transistor biasing circuit. That means in a transistor biasing circuit, proper zero signal collector current should be maintained, proper minimum VCE should be maintained, and Q point should be stabilized. So how we can measure the amount of stabilization, or how we can measure stabilization? If we are constructing a transistor biasing circuit, we have to analyze the circuit and find how much is the stabilization in the circuit. To find the amount of stabilization in a circuit, we are using a particular term or particular quantity that is known as stability factor. So stability factor is a factor for determining the stabilization, or how much stabilization is achieved in a circuit can be find out using the stability factor. So it is the ratio of change in collector current. Stability factor is denoted as capital S. So stability factor is defined as it is the ratio of change in collector current. So it is denoted as DIC. Change in collector current with respect to change in collector leakage current. So it is denoted as ICO. Collector leakage current. It can also be written as ICO, but here it is written as DICO. DICO means collector leakage current at constant IB and beta. At constant IB and beta. So this is known as stability factor. So stability factor is defined as the ratio of change in collector current with respect to the change in collector leakage current at constant IB and beta is known as stability factor. Now we have to find, or we have to derive a general expression for stability factor. So we are going to derive a general expression for S. General expression for the stability factor. So we begin our derivation with the equation IC is equal to beta IB plus beta plus 1 ICBO, or we can write in this definition we used ICO, so you can put ICO. So here let us assume that we are assuming that beta is independent of IC. That means beta is not varying with IC because we are finding the stability factor. So we are assuming that beta is independent of IC. So we are differentiating equation 1 with respect to IC. So differentiating equation 1 with respect to IC, we will get DIC by DIC is equal to, now beta is constant because beta is independent of IC. So beta is taken out, beta into DIB by DIC. Because IB is a factor which depends on IC. So we can differentiate that. So beta IB can be differentiated as beta is a constant. So beta is taken out, beta into DIB by DIC plus beta plus 1 is also a constant, beta plus 1 into DICO by DIC. Now DIC by DIC is 1 is equal to beta DIB by DIC plus beta plus 1 into DICO by DIC. What is S? S is defined as DIC by DICO. That is the ratio of change in collector current to the change in collector leakage current. So what is 1 by S? 1 by S is DICO divided by DIC. So we can put DICO by DIC as 1 by S. So from that we can derive the expression for S. So S is equal to, so we can rearrange this equation. That means 1 minus beta DIB by DIC is equal to beta plus 1 divided by S. So S is equal to beta plus 1 divided by 1 minus beta DIB by DIC. So this is the expression for stability factor in terms of beta and IC and IB. So in this expression it is clear that the value of S depends on beta and the variation of IC with respect to IB. So in the next session we are going to discuss about the biasing circuits. We are going to discuss about the biasing circuits or the method of biasing. We are using or we are studying three main biasing circuits or three methods of transistor biasing in detail, and we will calculate the stability factor in each case. In each circuit we will calculate S, and from that we can conclude that which one of the method is the best one. So we calculate the value of S, and if the stability factor from, we know that S is equal to DIC by DICO. So if DIC is equal to DICO, it means that if ICO is changing, IC is changing. Similarly, that means variation in ICO will cause similar variation in IC. That means DICO by DIC by DICO is equal to 1. So S is equal to 1 is the best stabilized circuit. The circuit having S is equal to 1 is the best circuit or best stabilized circuit. So this ratio indicates that, suppose if DIC by DICO is equal to 100. So that means DIC is equal to 100 times DICO. It means that if any variations occurring in DICO will cause 100 times change in DIC. I think you now understand the significance of stability factor. If DICO is 1, that means if change in ICO is 1, then DIC is equal to 100. So this means that IC is changing 100 times. So it is a very unstabilized circuit. But instead, if DIC by DICO is equal to 1, it means that DIC is equal to DICO. So that means any particular change in ICO will change IC, but it is the change, or it is not much changing. So the best stabilized circuit is S is equal to 1. So we will find the stability factor in each circuit, in each biasing circuit, and we will find the best stabilized circuit. So that we will discuss in the next session. In today's class we discussed about transistor biasing, the definition and purpose. So it is the proper flow of zero signal collector current and maintenance of proper collector emitter voltage during the passage of signal. So the basic purpose of transistor biasing is to make the input circuit forward biased and output circuit reverse biased. And we have two types of transistor biasing. One method is by introducing a bias battery, and second method is using biasing circuits, which we will discuss in the next session. Now, the inherent variations of transistor parameters means that the transistor parameters current gain beta and VBE will change due to the unavailability of advanced manufacturing techniques. So, if base width is varying, it will change the beta and VBE, and it will cause the change in operating point. It will lead to unfaithful amplification. So our point is that we have to make Q point independent of transistor parameter variations. So it will achieve using stabilization. So what do you mean by stabilization? It is the process of making operating point independent of temperature changes or variations in transistor parameters. So we know that Q point is IC and VC. So if IC is varying, it will affect the Q point. IC will vary when inherent variations occurs or when temperature changes. So the need for stabilization is 3 points. Temperature dependence of IC, that is clear from this equation. IC is equal to beta IB plus beta plus 1 ICBO. If the leakage current is changing, it will affect IC. So temperature, IC is dependent on temperature. So so we need stabilization. So next is the inherent variations beta and VBE. So we need stabilization. And third one is thermal runaway. That means since IC is dependent on temperature, when temperature is changing, it will develop heat inside the transistor and it will cause a self-destruction of unstabilized transistor. It is called thermal runaway. So we need a biasing, or we need a stabilization. So the essentials of a transistor biasing circuit is 3 points. First one, we need to ensure proper zero signal collector current in the biasing circuit. Next, we should ensure that the proper minimum VCE should be maintained in the biasing circuit. And third one, the biasing circuit should be stabilized, and it should ensure the stabilization of Q point. So, how we can measure stabilization? It is measured using the stability factor. Stability factor S is the ratio of change in collector current to the change in collector leakage current at constant IB and beta. So we have derived a general expression for S. It is S is equal to beta plus 1 by 1 minus beta DIB by DIC. So using this we can discuss biasing circuits in the next session. Thank you.